AP Physics 2, 2018, question number 1. You have a loop of wire entering a magnetic field. You have to explain the current flow and the direction of the current flow. There's three basic principles: Faraday's law, which I basically outline here in my first statement. You don't need to put this up here at the top, but I'm using Faraday's law, Ohm's law, and Lenz's law. If they see that, they already know that you know what you're talking about. But according to Faraday's law, the induced voltage, which is symbolized with this letter, it's also delta V, same thing, potential difference, is proportional to the time rate of change of the magnetic flux, B dot A, in that loop. Well, at times T1 and T2, the rate of change of flux is the same because the loop is traveling at the same velocity towards the right. Therefore, it's the same induced voltage, and since both loops have it's the same loop with the same resistance, they have the same current. According to Ohm's law, I equals potential difference over the resistance. Then you have to identify that at time T3, there is no induced voltage and therefore no current, since there is no change in flux in that loop. It's completely in the field. Then Lenz's law gives you the direction. You can't say, okay, Lenz's law gives me the direction. I have to say what it is. That the induced voltage will oppose the change that's creating that induced voltage. Well, at times T1 and T2 again, there is the same increasing flux towards the floor. So the current will flow counterclockwise. When the current flows counterclockwise, that creates magnetic flux towards the sky, out of the page, to counter the increased downward flux as a result of the movement of the loop. All right, in part B here, part I is pretty straightforward. Down here I have it solved, just basically plugging into the magnetic force equation, F equals QV cross B. You can leave off the sign of 90 here. If you put it in, it might be better, but this will be full credit. They just give you the three numbers, you multiply them to get the magnetic force. Then the magnetic force, part 2, or II, and you don't need to do this calculation, but it helps me now and in the future here. But bottom line is the magnetic force, according to the right-hand rule, as the proton enters, the force will be up towards the top of the page, so it'll start curving. The force is always perpendicular to the path, so that force, once again, cannot speed it up. It can only deflect the proton into a circular path of a certain radius that once again, I did the calculation down here like we've done before. And it can do no work. It cannot give it any kinetic energy. There's no work done by this magnetic force. The magnetic force never does work on a charged particle, just deflects them into a different path. So here's the math that shows you that if you have a bigger velocity for the same mass, same charge, same magnetic field, you get a bigger radius. So this basically helps you with part 3. Didn't need to do this, but you had to show the path here clearly. The path 2 has a bigger radius than path 1. And finally, and you could have drawn it on well, be careful, don't just draw this on a diagram because it's going to make the diagram very messy, but the electric field then force has to be towards the bottom of the page. You probably could have said in the minus y direction, but they give you full credit for saying towards the bottom of the page, because it has to be opposite the force, the magnetic force, which is towards the top of the page as the proton enters. The magnetic force is towards the top of the page, plus y. The electric force has to be towards the bottom, and electric fields are defined in terms of positive charge. So bottom line here, here's the electric force for, or the electric field for a constant electric field, E equals F over Q, or definition of electric field strength. So the electric force is E times Q, and the magnetic force we know is QVB, so you just set those equal, the Q's cancel, and then you plug in the velocity in the magnetic field, you get 9,000 newtons per coulomb of force towards the bottom of the page.